This movie covers subtopic 6.3, Photochemical Smog, under the main IB ESS topic 6, Atmospheric Systems and Society. Significant idea number 1. The combustion of fossil fuels produces primary pollutants, which may generate secondary pollutants and lead to photochemical smog, whose levels vary by topography, population density, and climate. You'll hear two different types of smog referred to. Industrial smog is formed by the combustion of fossil fuels. Photochemical smog, the topic of this subtopic, is formed when ozone, nitrogen oxides, and gaseous hydrocarbons produced from burning fossil fuels interact with each other and strong sunlight. Photochemical smog can be a mixture of about 100 different primary and secondary air pollutants. Primary air pollutants are produced from the combustion of fossil fuels, and they include carbon monoxide, carbon dioxide, black carbon, soot or unburned hydrocarbons, oxides of nitrogen. Take note, oxides of nitrogen are written with this X to represent the many types of oxides like NO, NO2, and so forth. Also, oxides of sulfur. As I mentioned, primary pollutants react with each other in strong sunlight to produce secondary pollutants, contributing to photochemical smog. Pictured here is smog over Shanghai, China. Primary pollutants can also be in themselves dangerous before even creating these secondary pollutants. For example, let's just talk a moment about soot, a primary pollutant. Soot is carbon particles resulting from incomplete combustion of hydrocarbons. Its color is black, and therefore it's called black carbon in some circumstances. Soot contains polyaromatic hydrocarbons, or PAHs, and heavy metals. Note that soot is not water-soluble. Since soot particles are so tiny, they bypass our natural ability to expel larger particles through coughing and sneezing. And since soot particles are not water-soluble, when they are inhaled, they lodge deep in the lungs and enter the bloodstream, leading to heart attacks, cancer, and even death. Polyaromatic hydrocarbons and heavy metals that are in soot are also toxic. Soot also absorbs solar light and warms the atmosphere, contributing to global warming. Furthermore, when it settles on the ice, it results in the ice absorbing more sunlight. Thus, soot contributes to melting glaciers and further contributes to global warming. Volatile organic compounds, or VOCs, are compounds that are easily become vapors or gases. That's what volatile means. VOCs are released from burning fuel, such as gasoline, wood, coal, or natural gas. They are also released from many consumer products. Some of them are listed here. On their own, volatile organic compounds have negative impacts on human health, such as asthma, itchy eyes, sneezing, and runny noses, and headaches. And with long-term exposure to them, kidney damage and elevated blood pressure can result as well. However, volatile organic compounds can also react with nitrogen oxides in the presence of sunlight to form particulates and tropospheric ozone, a secondary pollutant which is the main component of smog. In the presence of sunlight, secondary pollutants are formed when primary pollutants, such as VOC, like I already mentioned, undergo a variety of reactions with other chemicals already present in the atmosphere. And these secondary pollutants include tropospheric ozone, volatile organic compounds, PANs or perioxyacyl nitrates, aldehydes, carbon monoxide, nitrous oxide, sulfuric acid, and nitric acid, which are components of acid rain and will be discussed in topic 6.4. Tropospheric ozone is an example of secondary pollutant formed when oxygen molecules react with oxygen atoms, remember, oxygen atoms, that are released from nitrogen dioxide in the presence of sunlight. Like I mentioned, Volatile organic compounds also contribute to the formation of ozone. Essentially, these primary pollutants, nitrogen oxides and volatile organic compounds, bake together in direct sunlight to form ozone. Tropospheric ozone is highly reactive and damages crops, forests, and plants, irritates eyes, creates respiratory illnesses, and damages fabrics and rubber materials. Remember, smog, pictured here, is a complex mixture of primary and secondary pollutants, of which tropospheric ozone is the main pollutant. Tropospheric ozone precursors can be carried around the globe, making it a transboundary pollution problem. Tropospheric ozone warms the atmosphere and contributes to global warming. Tropospheric ozone damages plants and affects agricultural production by reducing photosynthesis, reducing the plant's ability to sequester carbon, reducing health and productivity of crops. Tropospheric ozone also causes over 150,000 premature deaths every year and millions more chronic diseases, particularly in children and the elderly. And so you can see how tropospheric ozone gets its name, bad ozone. Smog is a complex mixture of primary and secondary pollutants, of which tropospheric ozone is the main pollutant. The frequency and severity of smog in an area depends on local topography, climate, population density, and fossil fuel use. Here is a snapshot of air quality index values taken across the globe to give you an idea of the variations in severity of smog. You can see air quality ranging from good to very unhealthy and even hazardous. And as you can imagine, this does depend on topography, climate, and population density, and of course, fossil fuel use. Deforestation and burning may also contribute to smog. Thermal inversions also contribute to smog. Thermal inversions occur when a layer of warm air settles over a layer of cooler air that lies near the ground. Thermal inversion is harmful to the occupants of a city because when the warm air holds down the cool air, it prevents pollutants from rising and dispersing, which allows pollutants to build up to dangerous levels, as you can see pictured here. Temperature inversions play a major role of air quality in a city. These are especially dangerous during the winter because that time of year is when inversions are strongest. A typical inversion is measured by air quality index. The higher the air quality index during an inversion, the worse the air is for an individual. During these inversions, a major contributor to air quality is local wood stoves. This is an inversion in Salt Lake City, Utah, where I went to graduate school. Every winter, the city deals with thermal inversions. Smog is created around the city where the particulate matter in the air often exceeds national health standards. And the topography of this area, the mountain ranges surrounding it, contribute to this thermal inversion and the smog. Photochemical smog has significant impacts on societies and living systems. Health decline and subsequent economic losses caused by urban air pollution can be significant. According to the World Bank, air pollution has emerged as the fourth leading risk factor for deaths worldwide. While pollution-related deaths mainly strike young children and the elderly, these deaths also result in lost labor income for working-aged men and women. The loss of life is tragic. The cost to the economy is substantial. 1 in 10 deaths worldwide is attributable to air pollution exposure. And the loss of life due to air pollution is causing human suffering and reducing economic development. Look at these statistics. More than 6 times as many people die from air pollution each year than from malaria, and more than 4 times as many die from air pollution than from AIDS. Stop the slide and take a look at these graphs regarding air pollution. Pollution affects the health of people all ages, but when working age men and women die prematurely, their deaths also result in lost labor income for their countries. Look at this foregone labor income due to air pollution by region. It's affecting all over the world. Here you see an increase in labor income losses, again, due to air pollution. Significant idea number 3, photochemical smog can be reduced by decreasing human reliance on fossil fuels. Pollution management strategies include altering human activity to consume less. Example activities include the purchase of energy-efficient technologies, the use of public shared transit and walking or cycling. Regulating and reducing pollutants at the point of emission via government regulation and taxation. Using catalytic converters to clean exhaust of primary pollutants from car exhaust. Regulating fuel quality by governments and adopting cleanup measures such as reforestation, regreening, and conservation of areas to sequester carbon dioxide. How can we alter human activity at the first level of pollution management strategies? Well, we can change car habits. Simply drive less, maintain your car, and fuel up in cooler temperatures. And finally, purchase a hybrid or electric vehicle. We can change consumption habits. Avoid high VOC products. Avoid gas-powered yard equipment. Buy local and be energy efficient. You can take a stand. Don't support organizations that don't have good environmental practices. Promote your stance. Contact politicians and business leaders and be energy efficient. An example of regulating and reducing pollutants via government regulation, or the second level of pollution management strategies, is the U.S. Clean Air Act of 1970. It was a comprehensive federal law that regulates air emissions from stationary and mobile sources. Among other things, this law authorizes the EPA to establish national ambient air quality standards and to protect public health and public welfare and to regulate emissions of hazardous air pollutants. An example of the third level of pollution management strategies is of the Dutch designer Don Rosegaard, who created a 23-foot tall air purifier called the Smog-Free Tower. He created this in 2015, and the air purifier is being distributed in various places around the world. It is specifically created to be used in public parks as a local solution to air quality. You need to be able to evaluate pollution management strategies for reducing photochemical smog. So let's look at an example. Let's look at the success of the Clean Air Act. The U.S. vehicle pollution control under the Clean Air Act is a major success story in many measures. New passenger vehicles are 98 to 90% cleaner for most tailpipe pollutants compared to the 1960s. Fuels are much cleaner. Lead has been eliminated, and sulfur levels are more than 90% lower than they were prior to regulation. As such, U.S. cities have much improved air quality, despite ever-increasing population and increasing vehicle miles traveled. Furthermore, standards have sparked technology innovation from the industry. Here is a visual of the impact of the Clean Air Act. This is the air quality in New York City before and 30 years after the U.S. Clean Air Act. And there are economic benefits to the Clean Air Act. This estimate suggests that for every $1 spent to reduce emissions results in $9 worth of benefits to public health, the environment, productivity, and consumer savings. Here is a summary of this subtopic. This ends the movie for IBESS Topic 6.3, Photochemical Smog, under the main topic of IBESS Topic 6, Atmospheric Systems and Society. The slides were created by me, Dr. Nina Markham. Image sources are indicated with a URL under the image. If all images on a slide are from the same source, the source is simply cited at the bottom of the slide. Another resource for you is your IBESS textbook, whether in hardback form or online such as Cognity. Thank you for listening.